start, I'm very pleased to welcome you all into today Win for Peace webinar. My name is Kübra Aydın. I am one of the member of the Win for Peace group. And I am very happy to be moderating of this webinar today. This is a great opportunity to do this webinar with dear Eva. Our topic today is the nuclear fuel cycle. I'm looking forward to Eva's presentation. She is our leader, Win for Peace group leader. Also, she is a formal IAEA nuclear safeguard inspector. Today, we will talk about the nuclear fuel cycle, but before to start, I will present about our Win for Peace working group. And then Eva will take the floor and present the nuclear fuel cycle presentation. I would like to mention that if you have any question, please ask at the end of the webinar. We will have a Q&A session. You can just type in the chat box. We will answer all of them. Now, what is the Win for Peace group? What we are doing? I want to mention briefly about them. We contributed towards world peace through the involvement of the movement in the areas of nuclear non-proliferation, safeguard, export controls, and disarmament. We've coordinated activities across all four domains, in particular education and training, including webinars and hybrid events. Currently we have the 20 members from 4 continents. It's also open to if you want to join. If you are the member of Win Global, you can join us. You can just send an email to Eva, and we are happy to have in our group you. Thank you. Here our esteemed core team members, the photo of the volunteer esteemed members, Win for Peace. Our supporters is Vienna Center of Disarmament and Non-Proliferation, also United Nations Office for Disarmament Affairs at Vienna. What we performed up to now, the last year, we performed 7 webinars. It started with the foundation of international non-proliferation regime, safeguards basics, and national, regional, and international implementation experiences. And the last one is the nuclear propulsions. We performed these 7 webinars, and you can reach these recordings on the YouTube channel of the Win Global. Also, you can follow us on the social media. It is open to everyone: Facebook, LinkedIn, and Instagram. Or you can just send an email to us. What is our target? We planned the 10 webinar for these years. We performed 2 of them, first 2 of them. Now it's the 3rd webinar. We started nuclear weapons basics, safeguarding SMRs. Now today we will talk about the nuclear fuel cycle, and we will continue cybersecurity, nuclear physics basics, and nuclear weapon free zone. And we will continue treaty on prohibition of nuclear weapon. At that, we are planning to perform women-specific topics. And I really recommend you follow us. Our next webinar is 6th of May. It's for the cyber security issue. Now I want to give the floor to Eva. Without delay, Eva, the floor is yours.
Thank you so much, Kübra. Well done. So thank you for the warm introduction. And I would like to acknowledge Kübra as our today's moderator. Good job. And working in the background is Florencia Renedo from Argentina, who is one of our webmasters. So thank you for your support. Welcome everybody to today's webinar on the nuclear fuel cycle. And since all of you work in the nuclear field, I don't consider this to be much of new stuff for you, but rather I consider it to be a refresher, just to refresh our memory of what is the nuclear fuel cycle, some of the underlying processes and terminology. As Kübra has said, if you have any questions, please put them in the Q&A at the bottom of your screen, and we will address them after I speak. Although I don't mind, if you have an urgent need to ask a question, you can also do that during my presentation. So we will look at what is the nuclear fuel cycle, what are the main processes. We will also look at some waste issues and tackle the nuclear fuel cycle and safeguards. And since this is a rather long presentation, I have created a Kahoot. So I don't know whether all of you are familiar with Kahoot. It's a website that supports presentations with short quizzes. So I've developed a few questions for some of the chapters, which we will address whenever the screen shows it. And what you do is there's a QR code plus and the pin for this presentation, which you will access, and then there will be a question, and you can open it on your mobile phone by scanning the QR code or just by connecting to Kahoot and putting in the pin, and then you will answer the questions, and let's see who will have the correct answers at the end. And here is the way to log in, but you will also see it on the respective pages. So here is the display of the nuclear fuel cycle. And what is the nuclear fuel cycle? So according to the World Nuclear Association, it's a series of industrial processes where you convert certain material in order to make it suitable to generate electricity in a nuclear reactor, and also the management of the spent fuel afterwards. The nuclear fuel cycle, from the safeguards point of view, also leads to the production of nuclear material. And for those of you who work in safeguards, you know that nuclear material that is subject to safeguards is any isotope of uranium, thorium, or plutonium. So how does this work? In order to, first of all, be able to produce the nuclear fuel, you need to know where it is. So the first step in the nuclear fuel cycle is actually the exploration, where you look for either uranium or thorium. Once you have discovered where it occurs, then you need to mine it. The next step is to mill it. It means to crush the ore and put it into a mill and to refine it. Then you need to take the ore to a conversion facility, the concentrate to a conversion facility. And then depending on the type of reactor you have, if it's a natural uranium reactor, you convert the uranium ore concentrate into a natural uranium UO2, which is then converted into fuel. Or for most power reactors, you need to enrich it first. So you need to convert the natural, the uranium ore concentrate into UF6, send it for enrichment, and then you need to convert it into UO2 again to produce fuel. The fuel is then introduced into a nuclear power plant to produce electricity. And after that, it is discharged, and it is either stored in a spent fuel pond for a while and then put into dry storage or wet storage, or it is for longer storage. It's put into a deep geological repository. And in case you want to reuse some of the material that is still present in the spent fuel, you need to reprocess it, which is a process where you separate the uranium and the plutonium from the fission products. And in a subsequent step, you separate the uranium from the plutonium. So this is basically how the nuclear fuel cycle works. Let's also look at where nuclear material is produced. So in the mining step, you produce either thorium-232 or uranium-238. In the enrichment process, you raise the U-235 isotope, which is the fissile one, which you need for the fission reaction. And in the power plant, when you irradiate the fuel, you produce U-233 if you irradiate the thorium, or you produce Pu-239 if you irradiate uranium fuel. And last not least, if you want to separate out those two elements, you need the reprocessing step. So let's look at the concept of front-end and back-end nuclear fuel cycle. So everything in blue is the front end of the nuclear fuel cycle. So that's everything from uranium mining and milling to conversion, enrichment, and fuel fabrication. Whereas everything in green is the so-called back end of the nuclear fuel cycle. So that's reactor storage and disposal or reprocessing. And then you can see these arrows going going consecutively for the if you reuse the fuel. Then you may have also heard about open or once-through nuclear fuel cycle. This means that the spent fuel is not reprocessed, whereas in the case of a closed nuclear fuel cycle, the spent fuel is reprocessed. So let's look at, first of all, some properties of uranium. You may know that uranium has been named after the planet Uranus. It is a silverish metal, and it's the heaviest of all naturally occurring elements. It's very dense, and it was formed in the supernova billions of years ago. It's available practically everywhere on this planet with an abundance of an average of 2 grams per ton. It's even present in seawater, and it's possibly responsible for heating the Earth's core. The most common uranium isotopes are uranium-238, which is present with a natural abundance of 99.29%. The fissile isotope is uranium-235, which is present with only 0.71% in natural uranium. And you also have some small amounts of U-234. Let's look at some of the properties of thorium as well. Although in my presentation, that's what I would also like to say, I will more concentrate on the uranium fuel cycle. But thorium is also a very important element, which is even more abundant in nature than uranium, and which may be used in the future in case we ever run out of uranium, which is probably not the case in the near future. So thorium, contrary to uranium, exists in a single isotopic form as thorium-232 in nature. It decays very slowly. And it's also very insoluble. So not like uranium, which is present in seawater, it's mostly present in sands, but not in a diluted form. And it is fertile, so not fissile. So you can only use it as fuel in conjunction with some fissile material. For example, if you add recycled plutonium to it. And then you can use that thorium fuel to breed the fissile uranium-233, which then can be used in some types of nuclear reactors. In the periodic table, you can see at the bottom, the last line are the so-called actinides, which start with actinium. And then you can see thorium as the second element in that row, palladium, and then uranium. And you can see that uranium is actually the last naturally occurring element in the periodic table, and anything to the right of uranium is man-made elements. What comes now? So first of all, we need to look at exploration, then at mining and milling. So how do we explore for uranium? We may conduct some geological studies. Some countries also conduct so-called airborne surveys where they have preliminary satellite imagery survey and then use aircraft for a more detailed survey. There, once you are sure where the uranium is, or you can do a surface survey. There are also some hydrochemical methods where you look for radium, the presence of radon in certain concentrations, which are indicative of the presence of uranium as well. And once you are sure where your deposit is, you can do some well logging to determine the size of your deposit. We have basically 4 principal mining methods. So one is the open pit mining. The second one is underground mining. Then we have in situ leaching, and you can also rework the tails from a uranium mine. So what does an open pit mine look like? So you basically just drill a hole into the ground, and you can see on the left the schematic here. Here is the uranium ore, and here just the trucks come in, and the uranium ore is just brought to the mill directly from the ground. In the case of an underground mine, the ore is much deeper and it's not feasible to drill a hole, so you need to drill shafts. And then, first of all, a vertical shaft and then horizontal shafts into the mines. And as you can see on the right-hand side, these may be quite big operations. For example, this is from a photo from one of the Canadian mines. In the case of in situ leaching, you need a certain geometrical formation in order to be able to do this. First of all, at the very bottom, underneath the uranium ore, you need an impermeable layer. Then you have the uranium ore, and then in between you have a permeable layer. So what you do is you inject some leaching agents into the uranium ore, which dissolve the uranium as a liquid. And then you have production wells, which pump them up to the surface, and from there you take them to the mill and you do the subsequent purification, etc. So, of course, each of these methods has advantages and disadvantages. In case of an open pit, the advantages are that it's less hazardous and lower in cost and higher in productivity, but unfortunately it has a large environmental impact. An underground mine has a lower environmental impact, but of course the risk to the workers is higher in terms of radon exposure and the risk of a cave-in. And in situ leaching is safe for workers, of course, and it can be also used to mine lower grade ores. And there's no need to grind the ore anymore because it's already in a dissolved state. But the contamination can be quite substantial, and as I've said, it requires certain geological formations, and the recovery rate is also lower. Let's look at thorium mining. So thorium is associated with several other minerals. Actually, it has been detected in over 100 different minerals. And in most cases, it's also uranium that is associated together with the thorium in those occurrences. And thorium-bearing minerals tend to concentrate in the beds of beaches. Actually, the percentage of thorium found in its ore is generally greater than the percentage of uranium. So it's more cost efficient to mine. And one important source of thorium I would like to mention is monazite, which is a rare earth phosphate mineral and which has been used worldwide. It's present in beach sands and it's present all over the world, and it has been used for mining thorium and uranium as well. So let's now look at this milling of uranium. First of all, you need to crush and grind the rock to a small size, like sand size. Then you need to leach, add leaching agents to dissolve the uranium, and depending on the process, this can be either acid or alkaline. Then you separate the uranium solution from the waste solids, and then you do some solvent extraction for purification and concentration. Then you precipitate and dry the so-called yellow cake to recover uranium as a crystal. And then you package it in steel drums, and the product is uranium ore concentrate. It's sometimes called yellow cake as well, but it's not always yellow. I will tell you that in a second. So here's some of the equipment that is being used in mines. First, you need to crush and grind it. Then you need use this ball equipment for the milling process. Then you have this huge ponds for thickening, acid dissolution tanks, and the precipitate filtering. You see in this case, it's a real yellow cake. But yellow cake can actually, or uranium ore concentrate can be either yellow or black. If it's calcined, it's black. And to the bottom right, you can see the different colors that different uranium oxide compounds can have. So uranium can actually occur in many different colors. Let's now look at the major uranium producers. You can see that Kazakhstan in 2021 supplied almost half of the world's uranium, followed by Namibia and Canada and Australia. So Kazakhstan is really a huge producer and exporter of uranium. Now, ladies, we have the Kahoot. We will look at the first 5 questions, and I need to stop sharing and move to my Kahoot. So give me a moment, please. One moment. I had it on my other screen, but I need to share it here. Okay. All right. So I have now, let me share my screen here. Where's the Kahoot? Here. So I will now press the button Start a Live Kahoot. And as I have said, you either scan the QR code and connect to the Kahoot, and or you can also type in Kahoot into your browser and then display that pin that was displayed before. So let's try this. It's my first time of doing this, so let's hope all goes well. So let's start in classic mode. So here it's loading the game pin. So you can please scan in that code to connect, or use the game pin and create a name for yourself, which you can recognize in the game. Very good. And I encourage you all to join. It's fun, okay? And the questions are really easy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Come on, everybody, join. Okay. Let's wait a few seconds. Florencia or Kübra, can you check how many participants we have? We now have 18 for the Kahoot.
We have 23 participants online.
So no missing, unless that's us. I think that's us. Yeah. Okay. So ready? I press the start button. Then comes the first question, and you just be careful how to press the buttons. Okay, I think it should be quite easy, but just be careful that you don't make any mistake when you press it. Okay. So ready, steady, go. First question. Does the front end of the nuclear fuel cycle include uranium enrichment? You have about 20 seconds, right? Hurry up. Okay, so I had 9 answers and 8 answers. So does the front end, remember that drawing of the where we had the colors in blue and green? So enrichment is at the front end of the nuclear fuel cycle, and anything starting from reactors is the back end of the fuel cycle, okay? So the correct answer is yes. Next chance. Ready, steady, go. Okay, we have the scoreboard. We have Verka, Phoenix, and Aigun. Okay, ready for the next question? 1, 2, 3, go. So, thorium is more abundant than uranium. Is this correct or wrong? So, remember my one of the last slides, I said that thorium is more ubiquitous or more abundant on the Earth than uranium. So the correct answer is true. So let's look at the scoreboard. Aigun has overtaken Verka and Phoenix is number 3. Okay. Very good. So, ladies, next one. Ready, steady, go. Which uranium mining method has the highest radiation exposure for the workers? Before you answer, think where the worker is. Is it open pit mining? Is it underground mining? Is it in situ leaching or tails reworking? Just think where the miners are and where they are most exposed. Okay. So the correct answer was underground mining. And we have Aigun, Verka, and Phoenix again. I think the others need to work harder to beat any of these 3 ladies. So let's go for the next one. Ready, steady, go. Is this true or false? Uranium ore concentrate is always yellow? Think of my last slide. Very good. So, as you will remember, if it's yellow cake obviously is always yellow, but uranium ore concentrate can be yellow or black. So we have Phoenix overtaking Verka. Aigun is still on the top. And we have some followers. So very good. Let's go to the next one. So the question number 5, Kazakhstan is the world's largest producer of uranium. That should be pretty easy. Okay, correct. So if you remember the last slide, the figures of 2021, it was Kazakhstan who had almost 50%, 45 point something percent. So that's a true statement. Okay, we will continue here after we continue with the presentation. So I stop sharing now and keep your Kahoot somewhere running in the background. And let me share the other screen. Okay, so this is where we were. And we now continue and look at what comes next. The conversion step. What is uranium conversion? Actually, conversion is plain chemistry where you purify the uranium or concentrate and convert it to a chemical form, which you then need for the next stage of the nuclear fuel cycle. And as I have said before, this depends on the type of reactor that would use that uranium ore concentrate. If it's a reactor that uses natural UO2, you convert it from uranium ore concentrate to UO2, natural UO2 without the enrichment. And this is for reactors that use natural UO2, like, for example, pressurized heavy water reactors. And of course, there are also the old type Magnox reactors where they use the natural uranium metal, but I don't think there are any more running now. So in this case, the UOC will be converted to UO2 powder and sent to a natural uranium fuel fabrication plant. In the most other cases, like for pressurized water reactors, boiling water reactors, etc., you need to enrich the uranium first. And that means you need to convert the uranium ore concentrate into natural UF6, which is the feed for the enrichment process. And after the enrichment, the UF6 will then be converted to UO2 powder for feed into the LEU, low enriched uranium fabrication plants. So remember, either natural uranium, then you just need UO2, or enriched uranium, you need to first go via the UF6 and then the UO2. Here's a schematic of the whole process. So first you take the U3O8, dissolve it in nitric acid. It's quite impure, so you need to purify it, precipitate it, reduce it, calcine it, hydrofluoridate and fluorinate it, and the final product is then UF6. Let's look some of the properties of UF6. So UF6 is actually quite reactive and corrosive, so it needs to be handled with great care. It also requires materials that can withstand the UF6. So UF6 is stored and processed either in stainless steel or aluminum alloys, nickel and nickel alloys. It also poses a chemitoxic hazard, so you have to be careful not to inhale it. And it has some interesting properties depending on the temperature and the pressure. It can be either solid at normal temperature and pressure, or it can become gas if you heat it up. And you can see this triple point. That is a point where it can be either solid or liquid or gaseous. Let's look at some countries that run conversion facilities. So for natural uranium, these can be Argentina, Canada, China, India, Korea, Pakistan, and Romania, who have CANDU type reactors. And those who need to convert the UOC to UF6, you have Brazil, Canada, China, France, India, Iran, Pakistan, Russia, UK, and USA. Now, the next step in the nuclear fuel cycle is enrichment. You can say, as I've mentioned, in natural uranium, the U-235, that's the fissile isotope that you need for the fission reaction in the reactor, only occurs at an abundance of 0.71%. So you need to physically increase that concentration, and enrichment are all the processes that increase this U-235 isotope in the uranium. And you need multiple stages to reach the required level of enrichment. And then the enriched UF6 is used as a feed material for reactor fuel fabrication. For power reactors, this can be an enrichment of up to 5%. In research reactors and some of the new reactor types, you use enrichment up to 20%. And for those of you who work in safeguards, anything that is 20% or above 20% is considered highly enriched uranium. Once the enrichment is higher than 90%, this is considered weapons grade uranium. So you can use it for weapons, nuclear weapons. There are several technologies, enrichment technologies. The very first one that was used was gaseous diffusion. Then centrifuge enrichment. You can also use lasers for enrichment. So there's the molecular laser isotope separation, or the atomic vapor laser isotope separation, and the Australian process SILEX. You also have aerodynamic separation and several others like chemical, etc. And as I've said, all techniques use these slightly different masses of the uranium isotopes U-238 and U-235 for the separation. Let's look at the most important one, which is the centrifuge enrichment. This process was developed already in the 1940s, but the diffusion process was a little bit simpler, and that's why it was used first. But nowadays, 95% of the enriched uranium is produced with gas centrifuges. Gas centrifuges need to be very resistant because they need to run about 25 years continuously without stopping. And the centrifuges are arranged in so-called stages, and a large number of them in parallel. And those stages are then arranged in cascades. So as you can see from the schematic, you feed the natural uranium hexafluoride gas on the top. Then it runs down the centrifuge, and the lighter U-235 separates and rises to the top, whereas the denser U-238 sinks to the bottom. The enriched stream is fed to the next centrifuge on the top, the depleted stream at the bottom to the next stage, etc., etc. So this is how enrichment works in simple forms. Let's have a look at the uranium enrichment plant. So if you remember the phase diagram of UF6, first you need to heat up the UF6 to turn it into a gas. Then you reduce the pressure. Then you feed it into the centrifuge cascades at the center of the cascade. On the top of the cascade, you have the enriched stream, and at the bottom you have the depleted stream. So this runs through many cascades, and once it has reached the up to 5% level of enrichment for reactor fuel, you collect the enriched UF6 in so-called cool boxes in UF6 cylinders. And from there, they are taken to the fuel fabrication plants. And at the bottom, you compress the depleted stream and also collect it in depleted uranium UF6 cylinders, which are then stored somewhere, and they can be used for things like conversion to uranium metal for shielding, etc. Here's a look at the different types of centrifuges. You can see they can be either very high or very small, stacked on top of each other, or anything in between. And here is a photo of a cascade. So you can see these large amounts of centrifuges connected. And here you can see the header piping. So it's a very complex process. Here is a chart from the WNA on how you enrich 1 ton of natural uranium feed. On the x-axis, you can see the enrichment, the percent of U-235. On the y-axis, you can see the effort that is required for enrichment. It's called so-called SWU, separative work units. I'm not going to go into details about that. But as you can see, if you want to enrich from the 0.71% to say 5%, you need a lot of effort. Whereas then to enrich from the 5% to the 20%, less effort is required. And then to enrich from the 20% to the 90%, even less effort is required. This is what I want to stress with the enrichment. So at the beginning, you need a lot of effort, but as further you go in the enrichment, you need less efforts. There are about 14 countries that have enrichment facilities, and I'm not going to read them out to you. And let's now go to the next step, which is fuel fabrication. So this is also an industrial process. You now know that the input is either enriched UF6 or natural UO2. So you have that UF6, which you first need to convert to UO2. Then you need to produce the pellets. Then you put the pellets into rods. Then you assemble the rods into fuel assemblies or into canned fuel bundles, depending on the reactor type. In the case of the fuel fabrication process, you start with, let's now look at the enriched process. Here you start with the UF6 cylinder. Then you need to convert it into the UO2. Then you need to put it into a press, pellet press. Then you sinter the pellets, you grind the pellets, you put them into the pins. Then you scan those pins and check whether they are not leaking. Then you assemble them into the fuel assembly. Then you inspect them and then you dispatch them to the reactor. This is basically a simple process, a simple summary of the process. There can be different fuel types. So as I've mentioned, the PHWR, so the pressurized heavy water reactor fuel bundle. But you can also see the PWR fuel assembly, the BWR fuel assembly, or the VVER fuel assembly, which have different amounts of pins inside the assembly. So let's next move to the reactors. So here's a schematic overview of a reactor. As you can see to the bottom left, you have the reactor core, where the fission reaction takes place, and where heat is generated through the fission reaction, which is transferred to the steam generators, where steam is formed. The steam then goes to the turbine and turns the turbine and the generator converts the steam into electricity. The steam is then routed to the condenser, where the cooling water removes the excess heat, and the steam is condensed into water, which is then pumped back to the steam generator for reuse. So it's a circular process here. Let's look at the basics of the most important power reactor types. So you have the pressurized heavy water reactor, which I have mentioned. You can see here that the core is actually not a core as you would expect in the other reactor types, but it's a so-called calandria, where the fuel bundles are put into those tubes inside the calandria, and the control rods are moved from the top to the bottom. And one specific of the heavy water reactor is that it does not need to be shut down for refueling, but there's a constant refueling as required. So it can be operational all the time. In the case of a boiling water reactor, the water is allowed to boil, otherwise it's the same process. And in the pressurized water reactor, the water in the core is not allowed to boil, but otherwise the process is also the same. Here's a look of the inside of the nuclear power plant. You can see the core with the red shield, and beside it is the fuel pond with the refueling machine and all the auxiliary equipment at the back. Currently, or as of mid last year, we had about 436 nuclear reactors in operation in 32 countries, and here you can see the countries. Let me briefly mention research reactors because, of course, they also need nuclear fuel. So there are about 220 different types of research reactors operating in almost 60 countries. And their main purposes are to produce radioisotopes, to conduct the research for material science, to test materials, and also for training of students, reactor engineers, etc. So, ladies, we go to the next Kahoot. So let me change again to the Kahoot. So, let me give you a few seconds before I open the Kahoot again. I hope you are all connected now. I think the next would still be the score. Okay, we have Igon. Igon, you are leading, but very just a few points behind you is Phoenix, and then Verka, somebody called Name, and Azel. So those names which are not showing, here's your chance. Let me press next. 1, 2, 3, go. CANDU reactors run on enriched uranium fuel. Is this true or false? CANDU reactors are pressurized heavy water reactors. Heavy water. Remember that?
Eva, we cannot see your screen, Kahoot screen now.
Sorry about that. Okay, I think we need to repeat this. Sorry about that.
Yeah.
Yes. So let's do that again. Resume. Okay, so let's go next. Pressurized heavy water reactors. Pressurized water reactors require natural uranium fuel, not heavy water, but pressurized water reactors. Do they require natural or enriched fuel? So the correct answer, pressurized water reactors require enriched uranium fuel. So this is false. Okay, let's look at the score. Verka on top, Igon third. Okay, we have RIE and NJ. So some people are catching up. Okay, next question. The mostly used method of uranium enrichment currently is gaseous diffusion, lasers, gas centrifuges, or aerodynamic separation. I said it during my presentation. Which one is the most common method? So the correct one is gas centrifuges. Let's look at the score. Verka on top, Phoenix, NJ, RIE, catching up. Ready for the next one? Is this true? In a uranium enrichment plant, the UF6 feed enters in the center of a cascade. Is this true or false? You look at think of the schematic that I showed you of the plant and the cascade. Okay, so that was the true statement. So let's look at the score. Verka leading, Phoenix, NJ, Valerian catching up, RIE falling behind. Next one. When enriching uranium, the most effort is required to enrich from 60 to 90%. Think of that curve. Is this correct or false? Yes, this is a false statement. The most effort is required at the beginning of the enrichment process, but the higher you enrich, the less effort is required. Okay, next question. So scoreboard. Okay. I think this is the score. Verka, Phoenix, NJ, Valorine, REI. Next one. The feed for a fuel fabrication plant for the production of the most common fuel types is natural UO2 or enriched UF6. Is this true or false? So this is the true statement. Yes, as I've mentioned several times, it's either natural UO2 or enriched UF6, which you feed into the fuel fabrication plant. The score is Verka, Phoenix, NJ. So now number 12, question number 12, which is the last one for this section. Ready, steady, go. In a pressurized heavy water reactor, fuel is exchanged without shutting down the reactor. Remember the slide with the calandria. Okay, that's a true statement. Let's look at the score. Verka, Phoenix, NJ. Okay, ladies, I stop sharing here. Very good. Let's now share the other one, the presentation. Okay. So we have now finished the enrichments. So the front end is finished. Let's now move. Okay, we've done that. Let's now look at the composition of spent fuel after irradiation in the reactor. As you can see, there's still a lot of useful stuff in that spent fuel. You have a lot of uranium still present, 96%. Then you have produced some plutonium inside the reactor, like 1%, and 3% are real waste, namely fission products, although maybe some of those fission products could be used for radioisotopes, but mostly it's considered to be high-level waste. So what are the characteristics of spent fuel? A spent fuel element is geometrically and structurally intact, so completely intact. If you look at it from outside, there's no difference to spent fuel or to fresh fuel, but it's highly radioactive, so it needs some shielding. It's also very hot, so it needs some cooling. And it contains many different radionuclides with different half-lives. Some of them have only seconds of half-life, and some of them have millions of years. And as I've mentioned, they contain still some valuable materials like, for example, uranium, plutonium, cesium, cobalt, etc. In a reactor, you also produce plutonium, which is a man-made element with the number 94 in the periodic table. And it's produced both in research reactors and in power reactors. And the half-lives of the plutonium isotopes can be between 14 and 375,000 years. So quite a difference here. And the composition of those plutonium isotopes in the spent fuel depend on the type of fuel, the time that it's irradiated, the uranium is irradiated inside the reactor, and the reactor type. At the bottom, I think you have all heard about low burn-up and high burn-up. So the burn-up is how long you leave the fuel inside the reactor. From a safeguards perspective, low burn-up fuel will contain a lot of plutonium-239. You can see that those figures in red on the left. And anything, any plutonium that has a burn-up, has a plutonium-239 of quantities greater than 93% are considered to be weapons grade. The longer you leave the fuel inside the reactor, the more different higher plutonium isotopes will be produced. And so-called reactor grade plutonium will only have smaller quantities of plutonium-239, but they are all under safeguards. But from a weaponization point of view, you would be interested in low burn-up reactor fuel. Once the fuel is discharged from the reactor, it's put into a spent fuel pond where it is stored for cooling for 2 to 5 years, depending on the capacity, etc. And so this is the spent fuel wet storage. After that, you have several options. So either you, after the cooling, you take it to another wet storage facility, or you store it in a dry manner, or you put it in a deep geological repository, or you reprocess the fuel to recycle some of its uranium and plutonium. This is just an overview about the dry storage, what a dry storage facility looks like, and the dry storage casks, and the size of the casks, and the shielding. And you can store them there for 40 to 60 years. Many countries are looking at the option of a deep geological repository, where the spent fuel is isolated in geological structures, and those structures are expected to be stable for millions of years, because don't forget the very long half-life of some of the radioisotopes still present in the spent fuel. They are both natural and natural and engineered barriers. So the natural barriers are water impermeable layers of rock, for example, clay, or gas impermeable layers, for example, salt. And then the engineered barriers are either bentonite clay or cement. Finland and its Onkalo facility are the most advanced facility of this type. And here's an overview of what it looks like, how deep inside. So it's more than half a kilometer inside the ground. And you can see on the right-hand side those green tubes, which is where the fuel will be stored. Let's now move to spent fuel reprocessing. So in this step of the nuclear fuel cycle, you separate the plutonium and the uranium from the fission products, and then purify these elements. And those separated plutonium and uranium isotopes can then be made into reactor fuel, recycled fuel, so-called MOX fuel, mixed oxide fuel, and it can be reused in the nuclear fuel cycle, in the reactors rather. So there are several methods, of course, for reprocessing. There are wet reprocessing methods, with the most common one, the Purex process. Then there are dry reprocessing methods like pyro reprocessing that uses high temperatures. And also other methods are under development for fast breeder reactors, molten salt reactors, etc. The most important process currently is the Purex process, which stands for plutonium-uranium redox extraction. You can see that in the reprocessing plant, the spent fuel is received in casks. It's inside the spent fuel pond. The fuel assemblies are removed from the casks and stored. Then they are taken to the chopping station, where the fuel assemblies are chopped up, and the contents are dissolved in nitric acid. In the next step is the separation step, where you separate the fission products from the uranium and the plutonium. The fission products are vitrified and stored safely. And in the next step, you can then separate the uranium and the plutonium and purify it. And on the top, you see the pure uranium process, where you can store the uranium as uranium oxide. And at the bottom stage, you can add the uranium to the plutonium and convert it to oxide, and then it's the so-called mixed oxide that I mentioned previously. There are several countries were running reprocessing facilities. Some of them are no more operational. I think at this stage it's China, France, India, Japan, Pakistan, and Russia who are reprocessing. All the other countries are not reprocessing or not reprocessing anymore. A brief look at low and intermediate level waste. That is radioactive material in concentrations or chemical forms which does not permit an economic recovery, and which therefore needs to be disposed of somehow. So you can either have an open disposal facility like to the left, or you can also dispose of the waste underground. Let's now look at some safeguards considerations. So not all radioactive material is subject to IAEA safeguards, and I mentioned at the beginning of my presentation which material is subject to IAEA safeguards. That's so-called nuclear material. That's uranium, thorium, and plutonium. There are two nuclear fuel cycle facility types that could produce weapons usable material. The first one is uranium enrichment, where you can enrich the up to 90% and above, which is considered weapons grade uranium, if you think of the enrichment process. Or spent fuel reprocessing plants, where you can separate the plutonium out and use the plutonium for nuclear weapons. So, ladies, we are coming to the last Kahoot, I think. So let me get out of here, and can you go back to your Kahoot again, please? Let me share the screen. So let me give you a few seconds. One, two, three, go. So the next 5 questions and the last 5 questions for this presentation. Ready, steady, go. Spent nuclear fuel contains elements that could be reused. Is this true or false? So everybody got that right. Bravo. Yes, of course. There's a lot of stuff inside the spent fuel that can still be reused. So let's look at the score. Verka leading, Phoenix and Jay. Are you ready for the next one? Ready, steady, go. Plutonium-239 is the most important plutonium isotope for use in a nuclear weapon. Think of the low. Very good. So that's a true statement. You need I mean, you could also produce a nuclear weapon from other plutonium, but the higher the isotopes of plutonium, the more properties they have that don't make them so good for using nuclear weapons. So it's mostly plutonium, low burn-up fuel, where you have a lot of plutonium-239 that is good for nuclear weapons. Next question. Ready, steady, go. Oh, sorry, scoreboard. Verka leading. Okay. So we go for the next one. 1, 2, 3. Spent nuclear fuel first needs to cool off in the spent fuel pond. That's a true statement. You can't just, when you remove the fuel from the reactor, it's very hot and you first need to cool it off before you can do anything else. And as I said in my presentation, you need to cool it for 2 to 5 years. Very good. Scoreboard. Verka still leading. Ladies, you need to try to beat Verka. So let's go for the next one. 1, 2, 3. The first deep geological repository is being built in Sweden, Finland, USA, or Russian Federation. Okay, Finland was correct. So Finland is the most advanced one in terms of nuclear deep geological repository. Let's look at the scoreboard. Verka, not much difference between Verka and Phoenix. Let's go for question number 17. Which radioactive material is nuclear material subject to IAEA safeguard? Uranium, thorium, products, plutonium. You have to select many, not some of them, right? Okay, uranium, thorium, plutonium. Fission products are not subject to safeguards. They are considered high-level waste and they go for storage. But the uranium, thorium, plutonium are subject to IAEA safeguards, no matter where they are. Very good. Scoreboard. Phoenix overtaking Verka. Okay. So this is now comes question. 2 more questions left. One more. Next question is 1, 2, 3. Oh, sorry, this is the last one. Which fuel cycle facilities can produce weapons usable material? Conversion, uranium enrichment, reprocessing, uranium mine. Got my last slide. Okay, very good. So to produce weapons grade material, you need either U-235 or Pu-239. U-235 is produced in a uranium enrichment plant and Pu-239 in a reprocessing plant. It's separated. Very good. So that was the last question. Let's now look at the winner. Woo! And 3, Verka number 2. Phoenix number 1. Wow. Okay, ladies, this was quite a thing. That was quite different from what we saw, huh? So, very good. Congratulations. I suggest, I don't know who is Phoenix, Verka, and NJ. Can you send an email and you will get a certificate, okay? Just write it down. Oh, bravo, well done. And actually, it brings me to the end of the presentation. And I would like to thank you for your attention. And I open the floor for Q&As. Oops, sorry, I need to the Kahoot because it makes too much noise. Okay. So thank you for your attention. I hand over to Kubra, who will lead the Q&A session.
Okay. Thanks, Eva, for your presentation. Also, the Kahoot is a great idea. Thank you. It was very fun to learn. Thank you for your fruitful presentation. We refresh our knowledge. Also, we had an opportunity to gain deeper understanding of the nuclear fuel cycle. Thank you. Now it's time to Q&A session. You can write your question. We encourage you, feel free to ask your questions.
May I encourage those ladies who didn't get some of the answers right? Maybe I didn't say things clearly. If you have any questions there, do let me know, please.
You can just type in the chat box your questions.
Wow,
Okay.
I'm happy. Okay, there's one question, I think.
We have now 4 questions, Eva.
Yes. Okay, so I can see, I start from the top. You mentioned that uranium can also be found in seawater. So far, have there been attempts to extract uranium from seawater? Yes, there have been. As far as I know, Japan has done such experiments and been successful. I don't think it's done on a commercial scale yet, but maybe as the uranium prices go up, it can become feasible to extract uranium from seawater. But I suggest, Catherine, you Google uranium extraction from seawater, and I'm sure you will get some results to see what is currently going on. A question by Safa. Hello, Safa. The next webinar will be on the 6th of May about nuclear security, in particular about cyber security, from our friend Rhonda Evans from the World Institute for Nuclear Security. So watch out for that. The announcement will be diffused very soon. Next question, Fernanda Almaguer. In a fusion process, the cycle is completely different. Yes. In the fusion process, you need a different feed material, and the process you fuse, you don't fission, but you fuse helium and tritium isotopes, so elements. So it's a completely different cycle, and also what comes out and the waste is completely different. So it's a completely different process. If you guys are interested in fusion, we could have a webinar on nuclear fusion. Let me just take a note of that. So I know some people who could tell us more about that. Okay. Veronica Zapasnik. So I guess Veronica is the number 2 of the score. So congratulations on that. Do you think that it would be more trendy to build new recycle facilities? Trendy to build new recycle. Do you mean reprocessing plants? If it's reprocessing plants, you must be aware that reprocessing always leads to separated plutonium. And as I have said, that is always a proliferation concern. And for example, the United States, many years ago, they abandoned reprocessing for non-proliferation reasons. So I know that some countries, especially the ones interested in fast breeder reactors and also the nuclear weapon states, for example, the Russian Federation, they are looking at reusing fuel in for example, fast breeder reactors, and then doing the reprocessing. So there are some new attempts for that, but I think this is restricted to some few states, and I don't think this will happen on a large scale, and it will always be subject to IAEA safeguards. Okay, comparatively, which has more safeguards, fission fuel cycle or fusion fuel cycle? Catherine, safeguards is applied to nuclear material, which is uranium, thorium, and plutonium, which does not appear in fusion. In fusion, you look at the light elements, whereas in the fission, it's the heavy elements. So it's the completely opposite end. So there is currently no safeguardable material in the fusion process. If that answers your question. I see another question. Where and how is high-level radioactive waste currently stored? So I have been to the La Hague reprocessing facility while for inspector training while at the IAEA. And as I have said, during reprocessing, you separate out, in the first step, you separate the fission products from the uranium and the plutonium. So the fission products are high-level radioactive waste, as you put here. It's the fission products. They are then vitrified to immobilize them and to make them non-reactive. And then they're put into drums and put into kind of stacks at that reprocessing facility. So they are stored like in a concrete protected environment. That's how they are stored, what I know. Okay, any more questions from the audience, from the participants? Dismiss, did I dismiss the question? I share you, oh, that was before, sorry, okay. So, any further questions? If not, then let me hand back to Kübra.
Okay. If you don't have any further question, now it's time to close our session. I would like to thank you, Eva, for this insightful presentation, and thanks to participants for their time and participation. Also congratulate the winners of the Kahoot quizzes, and I hope we will meet in our next session, 6th of May, cybersecurity session. Thank you. Have a nice day to all of you.
And me again, a big thank you to you, Kübra. You did very well. So applause for your moderation. And also thanks again to Florencia working there in the background to make it happen. Thank you, everybody.
Thank you.
I hope to see you on the 6th of May. Thank you. Take care, ladies. Bye-bye.